Live. Just give me a second. Okay, well, we are live now. So it's actually, I'll just check if things are okay. Yes. Yeah. Okay, Kanak, I'll just wait for 1 minute more for people to join in. I'm surprised by certainly a low turnout. I don't understand that, but just give me a minute. Okay. Okay. So we are going to start today. So it's a pleasure for me to sort of start this session of the Wednesday colloquium. And as usual, there is a treat for us today. We have with us an eminent scientist in the country, Professor Kanak Saha, from IUCAA, Pune, who is going to deliver the colloquium, the Wednesday colloquium today. I just wanted, before I formally introduce Professor Saha, I just wanted to say what the colloquium really has been standing for all these years. So the Wednesday colloquium has been sort of the a common playing ground for all the scientists within the institute, and it was envisioned by Professor Homi Bhabha, the director, the founding director of the institute, to sort of promote, crosstalk within the various disciplines in science, physics, chemistry, and biology. And the crosstalk would happen in presence of an eminent expert who would come to TIFR and deliver a colloquium style talk and sort of lead to a spur of discussion on one of the most interesting or challenging topics in one of the sub-disciplines in science. And this has been a tradition. Every 4 o'clock on Wednesday, the students and faculty members of the institute, they gather in AG66. But of course, in the world of Zoom now, we we all meet on Wednesdays. So we have an eminent expert amongst us, Professor Kanak Saha from IUCAA Pune, who is going to deliver today's colloquium. Of course, I do not have to restate, but Professor Saha recently won the Shanti Swarup Bhatnagar Prize in Physical Sciences for the year of 2021. So just a small biography on Professor Saha. So Professor Saha did his bachelor's with physics honors from Scottish Church College in Kolkata from 1995 to 1998. Apparently, he's my batchmate. And then he did his master's in physics from BHU Varanasi, which he completed in 2001. Once finishing his master's, he did his PhD in astrophysics, although he had dreams of being a biophysicist, but it seems he did his PhD in astrophysics from Indian Institute of Science, Bangalore, which he finished in 2007, which led to his interest in looking at telescope data, because in this PhD program he actually visited the Space Telescope Science Institute in Baltimore for a year. After finishing up his PhD, he went to do his postdoc in Geneva Observatory in Switzerland. Then he became a Humboldt Fellow at the Max Planck Institute of Extraterrestrial Physics in Germany, and also had a visit in Academia Sinica Institute of Astronomy and Astrophysics in Taipei. He started, of course, his independent position in IUCAA Pune in 2013, and currently is an associate professor. His research has been in looking at the dynamics of galaxies, very large-scale objects, both theory and simulations. And also, he's involved in observational astronomy because he's associated with so many telescopes, and focused on formation and evolution of galaxies. So, without further ado, I request Professor Saha to deliver his colloquium.
Thank you very much, Professor Dasgupta. It's really a pleasure to be with you and others here.
Yeah.
And
could you share your screen, please?
Yes.
Yes, that is also a little bit always.
Give me a second. Do you see my screen?
Yes, a full screen maybe, if you could do.
Yes.
Perfect. Thank you.
Yes. So thanks a lot for having me. So I feel really privileged. So in being included in your list of colloquium speaker, very special one. So I also without delaying today, I'm going to talk about one of my recent works, and basically the direction in which our group is working. And this is about extreme UV photons from high redshift galaxies. So my talk here today, as I imagined, this is the colloquium where I think in your institute, I believe there are people from other than astronomy, so may contain a lot of trivial stuff. So excuse me for that, and I'll try to keep it simpler and without equations and stuff like that. So that's the also. So a brief plan is now I give an introduction. So I thought there's a gap. So I thought maybe I'll take quite a bit of time for the introduction because it is required to build the ground. And then I quickly go into what we were been doing with Astrocyte actually. So that's majorly doing with Astrocyte and where it is now. And so to very basic, this is very so basic. So that we observe the light from the stars, and this is now very well known that the light from the stars, for example, sun, with the continuum, it follows the blackbody radiation very well. So it's can be described by a Planck's law, and which is characterized by a unique parameter, which is the temperature. And one can show that the Wien's displacement law, which is a simpler way to understanding the lambda times the lambda peak times the temperature, is a constant. So we can see that as the temperature goes up, the peak of the blackbody curve shifts towards the UV. And for sun, or which is about a few thousand Kelvin, to be precise, 5,500 Kelvin, the surface temperature, the peak is in the visible window. But if the temperature of the star is like, for example, let's say 80,000 Kelvin, the lambda peak would go at 362 angstrom. So this is the extreme UV photons. So in other words, there is a special like importance, which is that any light whose wavelength is below 912 angstrom, which is equals to if you look at the energy, it's 13.6 electron volt, which ionizes a hydrogen atom. So the any wavelength which is below 912, we can call this an extreme UV photons or ionizing photons, and also called the Lyman continuum photons. So my talk will be basically circle around this detection of such photons and why is it important and why we. So to look at other than the sun, so the stars, as you can see, these are like synthetic stellar spectrum on the right side. And you can see that the various type of the stars, as you go like from M, K, which is like cool stars, to like F, A, B, which is like very the hot stars. The synthetic spectrum also shows that the peak is shifting towards the left, towards the UV. And the interesting part here, which is very simpler, is that the stars which leave depending on its mass on this main sequence diagram. So the main sequence lifetime is inversely proportional to the mass to the power 2.5. So the massive stars live shorter life. So that's the one, which means that if we have O-type stars, which are like very massive, which are higher luminous, more massive. So they are they emit light very they are brighter. So and then also like live shorter. That's the message. Okay. Now when you look at beyond the Milky Way, we basically receive light from galaxies. Okay, and this is and galaxies are made up of billions of stars. For example, this is a Milky Way picture, which is very unusual looking, but made by a famous astronomer in 1785 by William Herschel, where sun is to be the center of everything, and that's the picture of the Milky Way. Whereas now, this is the current picture of the Milky Way galaxy, and where the sun is at the bottom from the center of the Milky Way to at 8.5 kiloparsec, and it goes in the around the center of the Milky Way at a speed of 220 kilometers per second, and it has a very definite orbit. Which makes it go around. So except like the Milky Way, as I said, when you look at the external galaxies, we only receive light along the line of sight. So this is the total light, integrated light. So this is all we have in astronomy, and this is what we use for our further analysis. Now, so that's just light. So now one can receive light in different wavelengths. So the different wavelength, if you look at the galaxy in different wavelengths, they carry different physics. And unfortunately, we are on the ground, we are very limited. So we have only the visible light pass through the atmosphere. And of course, like now there is radio, where we can study galaxies and then interstellar medium. But if you go to the shorter wavelengths, like we need to go to space. For example, UV is absorbed by the upper atmosphere, so we need to go to the UV. Here, so to look at a galaxy in UV, we need to go to space. Okay. Now here you can see this sort of like images of the galaxy, like taken in different pass band, for example. So some are optical, on the right side is an infrared, and if you go to the left side, which is like the bluer, this is an UV, okay, and this is in far ultraviolet. So what it means is that the appearance of the galaxy will also be very different in different wavelength, particularly in the far ultraviolet and on the higher side of the wavelength. And the far ultraviolet, as we said, that the wavelength is shorter. So the shorter wavelengths will be emitted by most massive stars, like O-type stars, where the lambda peaks in the shorter wavelength. And those those stars being massive, they will also be short-lived. So we are basically, if we see galaxy in far ultraviolet, then in a general sense, we can understand that the galaxy is forming stars now. Okay, that's the kind of the message that we want. So we can see that to understand the galaxies, like in a very like to understand the full picture, we need many different wavelengths, like sampling, right? So in a local galaxy, like in the local universe, it is like all easy. As you go to the higher and higher redshift, this gets difficult. That's where the crux of the problem. Now we can measure the redshift of the galaxy by looking at a spectral line. So one can look at, for example, hydrogen alpha line, Lyman alpha line, or like there are several strong lines which can be used to measure the redshift of the galaxy. There is also like other techniques when the spectroscopic observations become very costly. One can think about the observations in broadband, or like the sort of or medium or narrow band, and one can look at the band dropouts. For example, if you look at the galaxy in different pass bands, which is centered around different wavelengths, and one can think that, okay, this is where the galaxy is not there, there is no dot there, and suddenly it appears, and then it's like there. So which means that that the galaxy is basically dropped in that sense. So one can use that also to measure how far the galaxy is. So kind of the redshift. So I just show here because this is really this is just to give you a glimpse of what high redshift galaxies look like. So as you see the Milky Way's picture, which I think I forgot to tell, that this is not an actual image, but it's actually artistic impression with all the pieces of information put together, and this is the Milky Way. And you go to different redshift, redshift are marked by set equals to 0.5, 0.92, and as you go, you see the appearance of the galaxy also. Appearance of the morphology of the galaxy also becomes different. And if you go to the redshift around in the middle, where you can see like redshift of 1.6, 2.3, the galaxy is like with the clumps, okay? And not like the local galaxies where it's much more mature and bigger galaxy. So as you go to the higher and higher redshift, like 7, redshift 11.1 is one of the highest redshift galaxy. These are we can only do a very limited study from them, and let alone the fact that forget about the multi-wavelength, because it's really difficult. So we can only think about for example, these highest redshift galaxies are observed in the infrared band, more or less. So and then of course, as you probably have already heard several in talks, the James Webb Space Telescopes will do an excellent thing pushing this further end of the universe. So if you go to the higher and higher redshift, it's really become difficult to understand the full picture of the galaxy. And that's where the problem is, because if I show you here a picture of a tadpole and a frog toad, so one one wouldn't know if certain things were not understood. I try to compare with a galaxy at a very early universe, which is like a redshift 10, the very early universe. and which are redshift, the galaxy at redshift 0. So those galaxies must have evolved, okay, over time, right? Now, for the case of the biology, we know the full life cycle of that, and so we understand like no a lot. But what we don't know is the full life cycle of a galaxy. We have only one image at a given time, and for one galaxy, we don't have any other way to look at the life cycle of the galaxy. So often, like these studies become only in a statistical nature. So this is one of the biggest challenge of astrophysics now, to understand how from very early universe the galaxies evolved. Now, where is the connection to this? So I forgot to tell, I showed the Deadpool example because there is a lot of galaxy at a redshift around 2-ish and redshift around 1 to 2. There's a galaxy you can see, they look like a Deadpool morphology in a sense that there is a bright head and there's a tail kind of stuff, like a comet like stuff. So I thought I'll bring that analogy. So now with this we wanted to ask what type of galaxies would emit extreme UV radiation, because that's where we started and that's where we want to know where. So to understand this, we look at, let's say, the full timeline of the universe, and we won't go to the very early, but for us the interesting part is when it started after the recombination of the universe, which is redshift 1100, and when the protons and electrons sort of combined. So this is the recombined, and it became a hydrogen atom. And soon after that recombination era, the universe went into a dark phase, right? And those are the brief moment. You can see it is around from 400,000 years old to around 0.1 billion years old. So around this time, it was in a dark phase, and there were no stars and there's no galaxies. Okay, so soon, because of the instability in the if we believe in the dark matter halos, so the mini halos formed, in which allowed the first stars and the galaxies to form. And those first stars and the galaxies form from the hydrogen atom only, because there are very few metals, only helium and lithium, just from the Big Bang nucleosynthesis. So you don't, the first stars were probably thought to be very massive, like hundreds of solar mass, means 100 times more massive than the sun. And as you have learned, that the more massive the stars, shorter the leaf, and more massive the stars, they are also peak in the UV, okay, or extreme UV, because the most massive stars have the temperature will be also very high. So these are really like the O2 O series stars. So those stars would be you can imagine, since they're peaking in the very short wavelength, they would also be sources of the extreme UV photons. Okay, so we are talking about exactly the first galaxies, the first stars, or the first stars in the galaxy, which were basically sources of the extreme UV photons. And those extreme UV photons would come out of the galaxy, and the surrounding hydrogen atoms that were there, they started reionization, ionizing the hydrogen atom, and that led an era called the epoch of reionizations. As you know, many talks, and we have a lot of activity in the country and elsewhere in this area. And the question is what are those first galaxies? What are the natures? How do we know them?
Kanak?
Yes.
Just a quick question. I am a chemist actually by training. Yes. So I just wanted to ask, what is the sort of wavelength range you think you had in the deep UV photons, extreme deep UV photons?
which I'll come to in my talk down the line. So what we detected is at a 600 angstrom.
600 angstrom.
Yes.
Okay. Okay.
Yeah.
Okay. So yeah, sure.
Yeah.
Mm-hmm.
So that's the kind. So there is a lot of questions about the reionization. When did it started? How did it started? And when is it ended? What was the topology? All kinds of questions are here important. But for me, as an astrophysics, I wanted to know in terms of a detection, what kind of galaxies, what kind of objects they were. That's my goal. So now let's come to the bit more the understanding how these photons that we said, is it easy for them to escape? Okay, we know that those are the first galaxies which were producing the extreme UV photons. They must be also in somewhere else in the other galaxies. So this is a schematic diagram of on the left it's called the ionization bounded with holes, and on the right is a density bounded nebula. So it's like a star forming regions in the galaxy with a lot of intense star formation, and they will try to ionize the hydrogen. So as you know, H2 means Roman, the 2 is like ionized hydrogen, surrounded by there will be a neutral hydrogen layer. So that's the kind of basic or the structure of the Stromgen sphere, which is happening around the star forming regions where the lot of stars are forming. So now one can think about
sorry. Could you again define the two zones? H2 is what?
H2 is the ionized hydrogen.
Just ionized hydrogen. So H plus.
Hydrogen?
H
yes.
plus.
H plus. Exactly. The protons and electrons separated.
Right.
And H1 is a neutral hydrogen.
Neutral, just an atom itself.
Yes, atomic hydrogen. So this is basically the structure of the Stromgen sphere, and as you go to higher, there will be higher elements and things like in the local galaxies. Now one can think about if we talk about the ionizing photons, the photons whose wavelength is less than 912 angstrom or energy greater than 13.6 electron volt. So we know the cross sections of them follows nu to the power minus 3, and we can determine the mean free path of them. And the NH1 is the neutral hydrogen gas density, which is around 0.1 per centimeter cube, and one can easily get these numbers done, and comes out the mean free path is around half a parsec, whereas the size of the Stromgen sphere is around hundreds of parsec, depending on how massive the star is. Okay, now it looks like that these photons were produced at the source, they will not be able to escape the Stromgen sphere unless and until there are holes in that, okay, through which the photons will pass, or else the Stromgen sphere is incomplete. On the right side, where we say that okay, it's only H2, there's neutral hydrogen. So in a very intense star formation, they may happen like that. What is the real picture in terms of observations? We don't know. Okay, what is exactly happening in this? So there is a lot of favorism for the Stromgen sphere with holes at the moment. Okay, now to do this is a bit of a digression, but we did a recent work with one of my postdoc, which is called the Blueberry Galaxy, and using the state-of-the-art observation facility, which is called the integral field spectroscopy. And this is one of a kind in the local universe, and where we study the sulfur 2 versus the ratio of the sulfur 2 and H alpha, the hydrogen alpha line ratios. And we can see that on the first plot, around the region of the galaxy where we think there's an intense star formation, there is a low density of the sulfur 2 versus H alpha. And also the other lines like S2 over O3. O3 is doubly ionized oxygen. S2 is singly ionized sulfur. So in this,
quick question. So this is O3 at 6300 angstroms.
O3 is 5007 angstrom.
Okay. Yeah. And S2 is at?
S2 is a 6717 and 6731.
Oh, so you're using both the both the doublets.
Yes.
Okay.
Yes. Yeah, we also looked at like an S3 letter. So this is a very interesting paper. This is showing that in if you look at the bottom left, I don't have a cursor, sorry, and where I mark say the blueberry which is in the red curve, and inside there is a COS aperture, which is the HST cosmic origin spectrograph. Okay, in that we marked on the right side, which is called the dust map. This dust map is nothing but the ratio of the hydrogen alpha line and the hydrogen beta line.
Okay.
Versus like assuming the case B recombination case where the intrinsic ratio is 2.84. So we estimate the color excess, basically this E of B minus B. You can see that within the COS aperture, and one side there's a red, and one side there's a pink. It's a little bit different, but that's the so what we see here, there is a presence of the dust creating a scenario in which some part is like allowing to emit the escape photons and some part don't. So this is like a mixed type morphology that we are seeing, which is called the blister type morphology. So this is one of the first indication of actually the density bounded versus the ionization bounded the part and this is from the COS apertures we know Lyman alpha photons have escaped. So and this is only 10%. So we try to explain that. So anyway, so what I was talking about is the strongest sphere within the interstellar medium of the galaxy. Now imagine like with through holes, let's say some of the photons like manage to escape the interstellar medium, but in high redshift galaxies there are circumgalactic medium where the photons can get absorbed as well, especially those ionizing photons. And even if some photons like manage to escape the ISM, interstellar medium, the circumgalactic medium, there is a long path from the galaxy to us, and which is the intergalactic medium, and they can be also absorbed. They can also absorb the ionizing photons. So at the end, the ionizing photon that reach us to the telescope on your detector, it's very, very minuscule amount. So that's the state of the art. And here you can see that what I plot here on the y-axis is the IgM transmission. So as you go to the higher and higher redshift, the transmission falls like severely. So these photons that we can that most of the photons will be kind of absorbed. So that's it's a very difficult problem, and just to say that how the Lyman continuum photons. So there's a picture of the labyrinth where it shows that like I think every 2 years there is a conference on that discussing about the escape of the Lyman continuum photons, and I attended one in 2018 in Greece. So what we understand from all this is that the escape of ionizing photon itself is a very, very difficult, and that's where I think we came into picture, and that's where I'm going to talk about what we did. So what we did is with the Astrocyte that we basically observed the Hubble deep field or the Chandra deep field south, and to those like where for whom this is like new. So the deep field is like a patch of the sky with no bright star because otherwise it becomes difficult to go deeper and like the fainter observation. So we proposed this like very initially the two observation which is covering the good south region part of the sky is in the southern hemisphere near Fornax cluster, and we did it in 2016. There's an interesting thing, but I didn't want to like go. But 2016 also happened to be the I think I had my hard drive crashed, so I lost a lot of my simulation, the initial condition. So and because of laziness or whatever, I think it was not easy to recover them. And there was in this opportunity, I thought like, okay, this is a nice time to like change. Instead of like working on the which initial condition created what. So I gave up those research and I jumped into this, and it was very exciting for me. So we observed this in 2016 with Astrosat at about 100 kiloseconds. And with Astrosat, as you know, like there are two mirrors, which is NUV and FUV. And for this audience, I don't think there is a introduction required. And this was built, which is under the supervision of Professor Tandon, and in collaboration with IAA, IUCAA, TIFR, Canadian Space Agency, and ISRO. So we use two filters of the Astrosat, and far ultraviolet, which is centered around 1541 angstrom. So you can see this is the blue curve on the upper plot. And in the near ultraviolet, we observed with the NUV silica, where it's in the red big curve like this. So that's the pass band, we say. And this is the single orbit image. So we have about 40 orbit images. So I did those things by hand, because the pipeline was in a very initial stage at that time, and it took like about 2 years to like analyze this data, work on the pipeline, give input, and these things went on. And at the end, we created this image which is showing in the near ultraviolet in two fields that I showed. Okay, this image doesn't look very impressive, but I think you could like you will appreciate this soon. So this is a one orbit image, which is like looks like very pixelated. On the left side is the far UV, on the right side is the near UV. And this is what like sort of a zoomed in version of this on a part of the image in near ultraviolet, which is just called the Astrocyte EVD field, which we created. And this is as a very nice synergy with a lot of other telescope pointing. So, for example, what we show in the squares, in the blue squares are the HST pointing. Okay, and then there is the Muse observation on this, and you can see here this is the Hubble ultra deep field, which we created using Astrosat as well. So this is the image which is much better. And this what I did. This is a 4-color image, which is HST 814 and 435, and just a moment, and two filters of the Astrosat, basically the HST and Astrosat. So for this, HST has a different PSF, and Astrosat also like a completely different point spread function. So I did a PSF matching, so relief sampling, and both bring to the same thing, and that's how we created. What you see in these images are interesting part for me and for many of us are the fainter objects, like which is in blue here. And we reach a 3 sigma detection limit, which is half a magnitude higher than, half a magnitude like better than the HST. So we go up fainter level of 27.9 magnitude, whereas HST in the same wavelength range goes up to 27.4 magnitude. So this gives us a like sort of to look for fainter and further objects in UV band. And this is the Hubble the extreme deep field image, the same 4-color image. Now, before Astrosat, this is where it starts really by the science part where we are talking. So on the y-axis, which is the observed ratio of the flux FLYC, which is Lyman continuum photons, versus the F1500, which is at 1500 angstrom, flux at 1500. So the ratio. So in other words, this is a ratio of ionizing photons flux versus the non-ionizing photon flux. And on the x-axis, we have a redshift. You can see this entire plot was started basically 2016 actually. So, and then on the left objects, like the circles. The squares came from Chuck's tidal using cake observation on the 2018, when I had really almost finished the deep field. On the left side, at redshift around 0.4-ish, you can see these are the first few Lyman continuum photon observation from newly discovered galaxies called the green peas and the blueberries. And these are the high redshift galaxies. And in between this redshift range, between 0.4 to around 2.5, it remained called the Lyman continuum descent. There's another interesting part to look at into this. Each of these data points here are color coded. You can see the most of them are around 850 and above. Okay, so that is the rest frame wavelength of the photons that were received or that were measured. Okay, so we measure the Lyman continuum photons only when in such a way in the filter. Imagine our the Astrocyte filter has a lower wavelength side lambda1 and it's a lambda2 between like 2 lambda, like 2 different wavelength. There is a filter, and if the rest frame photons wavelength is such that if it is detected, it depends on the redshift. First of all, it depends on the redshift. So depending on the redshift, one can determine what is called the Lyman limit, which is 1 plot z, which is the redshift, times the 912 angstrom. So if we put redshift out of 1.4, which is the object that I'm going to discuss, then the Lyman limit comes around 2207 angstrom. And Astrocyte far ultraviolet filter, the red side, which is lambda2, is around 1800 angstrom. So entire wavelength, entire filter is within the Lyman limit, which means that all the photons that is received within this filter will be called Lyman continuum photons. In other words, in any source, detected in far ultraviolet in our image, and if it is coming from a redshift of around greater than 0.97, they will be within the Lyman limit, or they will be called the Lyman continuum photons. So this is the first detection that I'm going to talk very briefly here, and this is these are the people who contributed in this work. And so first I'll start with was it a serendipitous discovery? This is a fluke discovery, like lots of questions may come. So it is not like that. We did a systematic search, and it's in the paper, and we took around 1517 galaxies observed having spectroscopic redshift, okay, which is measured with the HST GRISM tape. We look for only in cases where hydrogen alpha, oxygen 3, and H beta line are available. And then we downsizing this sample, and at the end we were interested for some reason in the extreme deep field. We had only 38 objects, and of the 38 objects we had 2, and of the 2 we chose one which has a largest equivalent width, which H alpha and O3, and they are believed to be also the very highly star forming galaxies. So we chose them. So this is the galaxy. This is the part of the Astrocyte deep field in far ultraviolet. It's a very noisy looking image. So our detection was barely around 3 signal to noise 3. So you can see, like, we don't have a lot of photons here, and it's a weak detection, but that's it, like 3.2. But in the same location, if you look at in near ultraviolet, is a very strongly detected with a signal to noise of 10. So it's simultaneously detected in same location with the astrometric precision, whatever we could reach around 0.3 arcsecond. And in HST, as you can see, this is the HST part of the same part of the image in 2 filters, which is 154W. And it is just like the similar filter shape is similar. And in HST, this object was not detected with the HST, what with the observation they had. So we had this detection. And this is a multi-wavelength observation, since also being detected in Muse spectrograph, which we used for later study to using the magnesium 2 line around 2799 angstrom, and also use the O2, which is like 3726 O2 doublet, which was detected in that. And we see the GRISM, we had a very low signal to noise hydrogen beta line and a few spectral lines which helped us a lot. Now this is the clumpy galaxy. As you remember, I showed the high redshift galaxy. They look very clumpy. Okay. Now this is the HST image of the same galaxy that we're talking about. And you can see there are C1, C2, C3, and C4, 4 clumps. So in the very beginning, I was asked these questions whether the clump are they the same redshift? How do you know, right? So this is one of the questions like which came, and for which it helped us a lot using this HST GRISM 141 data from the 3D HST survey. We took the GRISM image. And you can see the GRISM image peaks in O3 and hydrogen alpha. These are low resolution spectrograph, like the only strong lines are useful in that. And that too also, like because of the low resolution, lines are often blended with the neighboring lines. For example, H alpha is blended with N2. So what we did actually with this GRISM data here, which is a 2D here, you can see in the 2D on the H alpha and O3, we looked at these things and do the pixel to pixel mapping from the actual image and the HST, the GRISM pixel and the HST observation. And then we did the emission line mapping with that. And then we look for the lines signature in C1, C2 clump, which is like almost at the horizontal, and C3 and C4. And in all the cases, we have spectroscopic observations where the H alpha, which is around 1.55 or something like that at that observed wavelength. This is a 6563 H alpha line. And we show that all the clumps having the same redshift. So this was also like a good achievement from our side, that we proved that the galaxy is having the same clumps, and all the clumps are at the same redshift. Then we also did quite a bit of modeling here. It is called the spectral energy distribution modeling, which is going from all the way from far ultraviolet wavelength, which is at the rest frame about 600 angstrom, all the way up to Spitzer, which is like the around 30,000 angstrom in this thing. So that this galaxy is not very large galaxy. This is the low mass galaxy, which is around 1.4 times 10 to the 9 solar mass, compared to the Milky Way, which is 5 times 10 to the 10 solar mass in stars. This galaxy is forming stars at a massive rate, around 55 solar mass per year, and low metallicity. We did also, as you can see, the model were not able to explain the far ultraviolet observation. So we tried with which is called the binary stellar population synthesis model, which is the BPAS modeling, and we come across a scenario in which we say that we need a low column density of the hydrogen gas, and also low dust, very low dust in that, so that ionizing photons could come out. So that was the thing, and this is one of the first kind at this redshift, which is between redshift around 1 to let's say 2, where the cosmic star formation history peaked actually. And we are finding a very good example of a galaxy emitting extreme UV photons in this redshift window. And in this redshift window, not only this galaxy, but also the other galaxies are also clumps. Like you can see, there are clumps in that galaxy. So this kind of opens up to the astronomers to look for or not close your eyes to the clumpy galaxies, because so far the detection was on the green peas and the blueberries. They are really, really tiny and undissolved almost. If you don't look at even with HST, many of them remain undissolved. So the clumpy galaxies are like a good head start in this sense. Now we calculate also the number of photons, and we are very close to my end of my talk. We calculate how much of these ionizing photons come out of the galaxy. So we use a KSB recombination standard stuff, which is like the follow the textbook. And first we calculate the number of ionizing photons that could not escape, means that were used in the dynamical equilibrium, which is in the recombination within the Strontian sphere. So since we have a strong hydrogen alpha line, which is like one of the Balmer series line, and we could use that line strength to estimate the number of ionizing photons that could not escape, means that were used. And then using the Astrocyte filter, we know that the entire Astrocyte far ultraviolet filter, whatever the light received or the photons received, that are actually ionizing photons, because that has a rest from 600 angstrom. So we definitely know. So we calculate how much photons that came out of this rest from 600 angstrom photons came out of the galaxy. And then the fraction of the photons is very simple. So it's basically the photons that were emitted divided by the photons, the total ionizing photons that were produced. Okay, and that comes cleanly around 0.2. Okay, if you assume that there is no IgM intervene, means the IgM are not like no. If you assume a mean IgM, the opacity, which is around 0.29, which came out from one of our analysis done for this study at this particular wavelength range, which is around 0.29 and which is around 20.25%. There are other ways also to estimate the escape fraction. So at the end, what I show here is the distribution of the escape fraction. Okay, so you can see that the escape fraction peaks around 0.2. This is in the second method, but our firm conclusion is that at least 20% of the Lyman continuum photons escape the galaxy, or the 20% of this 600 angstrom photons escape the galaxy. So with this, after the Astrocyte, we have 1 point here. Okay, and now you can see the very striking difference between the color. So all these are around 850 on this side of the plot, and we have a very outlier here at the 600 angstrom. Not only that, now I think one student in Geneva and one student here at IUCAA, they soon will be around 10 plus objects will fill this space here between this around redshift 1-ish. So this is a very ongoing and exciting work from our side. Now, what do we do with these 600 angstrom photons? There's a lot of implications here, and I wanted to touch one in which people are talking about this. You can see this is a recent model of the stellar by intrinsic stellar spectrum, where the stellar spectrum are really unconstrained on the shorter wavelength side, right? So, excuse me. So with a 600 angstrom data point here in this will give the way to constrain the ionizing spectrum of this model, and with more data points we can really constrain and try to understand, like, so there's like implications. Okay, and here I just wanted to do like sort of yet unpublished, And this is the first time I'm showing this, and looks like we have a very exciting detection at redshift 5.9, which is close to redshift 6. And this is the galaxy at an HST on the left side, and we have a detection with a very good detection in near ultraviolet filter with a signal to noise of 3.8. And the SED modeling is really exciting. It took me like more than a year now, and this is the Astrocyte data points here, and this is where the mark with the filters you can on the bottom, and this is where we are seeing sort of signature of probably POP3 stars. So if we don't use the POP3, we cannot explain the Astrocyte observation. So this is really exciting in many ways actually, because we are seeing at redshift 6 when we think the epoch of the reionization probably ended, and that's when we are finding a galaxy with a hybrid morphology. We have a POP3 some part, which is like the metal zero star spectrum, and on the right side, on the higher wavelength side, particularly in HST and covered by the Spitzer, they are also actually metal poor. We cannot explain this with the solar metallicity. Those are 10 to the minus 4 in terms of the metallicity unit, which is 0.02 for the sun. So they are also like sort of surrounded by probably metal pores stars and metal zero stars. This is a combination. So this is going to be really exciting. There is a lot of interesting point here. Also, we are probably hitting the helium ionization here, and that's going to be very exciting. So we have 3 objects. So we are in the process of writing this now. So I'm at the end of my talk now, and this is the future of the Astrocyte, the Astrocyte UVD field that I created. So you can see that the red, this curve showing the HST pointing, which means on this we have HST data, and these are the various pointings of the Astrocyte far ultraviolet filter. And you can see this like sort of square here at the end, which is the sort of intersection of all the pointings of observation. This is going to be the most UVD field, the ultra UVD field produced by Astrocyte ever, I think, and elsewhere as well. Nobody is going to have this DFD field in the next few years, definitely, because most of the UV missions are in the planning stage. And so that's going to be like exciting. So in the next coming few years, because this is producer like very good quality of data. And so these are the like sort of my team now. We have started collaborating with the Muse. Ronald Beko is here, and various students and postdocs. Like sort of this is increasing, and also like tons of collaborations in this, because we are sitting on a very unique data set at the moment by Astrocyte, and I feel very pleased that, and I'm very happy that I switched in 2016. And with this, I'm sort of ending my talk, and thank you for your attention.
Thank you very much, Kanak. Like everyone to unmute themselves, give a warm round of applause. Okay, so there are questions, Kanak. So Professor Devendra Oja, Devendra.
Yeah. Kanak, very nice talk. Thanks.
Thank you, Devendra.
Yeah, so I have just 2 queries. So you meant to say that for redshift greater than 1 and up to 2.5, there are only these compact star-forming galaxies are the Lyman emitters mostly, or?
So there are, I think I wanted to clarify. In Astrocyte filter, if I go, so you can see here, you see that there is the bluer side is around 1350 angstrom.
Okay.
On the redder side of the FUV filter, which is around, let's say, 1800 angstrom. If you divide 1800 by 912, so you get a 1.97. So minus 1, so it's like 0.97. So any objects that will have more than 0.97 will be entirely within the ionizing of the Lyman continuum photons. Now, I think that your question was, if I want to like see, is that the compactness, right?
Yeah.
So we don't have our object, which I showed you, is not compact. This is all actually clumpy. Because in Astrosat, we cannot resolve objects. So although this is what I wanted to show, we see only a signal here, but actual image looks like this in HST. So it's a clumpy galaxy. Okay, which is revealed by the HST, but we see only the net, like the photons, because we don't have that resolution. Okay.
Okay, thanks. My second query is about this Lyman continuum desert. So altogether, you have now some statistically good number of sources to talk about their luminosity density or something like that, or you have to still wait for that?
I think if you look at here, just go back to the plot here. So there are some fluke cases here on the cake side, because I think Chuck Steidel has revised this number. So, and here there are around like on the low redshift sides, we have around, I think 15 or so. And on the higher side, we have a 10. And so 10 plus like 25, we are adding soon around 15-ish. So this is, so I think should be possible to talk about the density.
Okay, thanks, Kanak. Thank you.
Okay, Kanak, there is a question in the YouTube. How was the nature of the first galaxies? How were the nature of the first galaxies, and how the extreme UV photons escaped from them?
If this were the first galaxy, so most likely, as we understand, if they are most massive stars, then if these are a few hundred solar mass stars, they must have been short-lived, so they must have gone for a supernovae explosion. So I believe, like around that, I'm not even sure there's a Storm sphere form. So the entire ionizing photons extreme UV photons will escape directly from there. So it is the problem of comparatively low redshift galaxies where we don't form POP3 stars, big stars, or the most massive stars, from where I think we have this issue where there's a Storm sphere and there's a layer of neutral gas there, so they would be. So but having said that, I wanted to also say that it's really difficult to answer because we do not also know, we don't have any model for how the first galaxy were. We only know that they could be POP3 stars. Okay, but if there is a POP3, then they must be very short-lived, a few mega year maximum. And then they would go probably supernovae blast, and then there is no question of I think neutral gas layer. So they would emit, they would escape, I think.
Okay. Thank you, Kanak. This was from Abhinav Chaudhary, who is a keen listener to our YouTube channel. Any other question from the Zoom audience? Students?
By the quantum efficiency.
Okay.
Okay, but the quantum efficiency generally goes down as you go into the shorter and shorter.
In the shorter and shorter wavelengths,
right? It's very
right. So what is the material? Do you know what kind of material they use to look at when they detect these photons?
I think this is a barium fluoride filter.
The filter is right. Okay, but then I
think it's a CMOS detector.
CMOS. Okay.
CMOS.
Yeah, so I think these are microchannel plates actually.
Microchannel plates. Okay.
CM.
Okay. Okay, CMA as Kulin. Yeah. Okay.
Okay.
Yeah, Kulinder Pal is telling us. Okay, fine. Thank you. Okay, any other a charge multiplier? Okay. Any other questions? Okay. Well, if there aren't any more questions, would like to thank once again Professor Kanak Saha for a wonderful. It's an open invitation from us. So, I would like to also thank everyone for joining in, and I just wanted to mention that we are going to take a break on the Republic Day. That means the next session is going to be on 2nd of February, and we are going to have a colloquium on data science by Dr. Ram from LBNL. So that the timing for that colloquium is slightly going to be in the evening at 6:30 p.m. But please join us on 2nd February for a very interesting colloquium on sort of deep learning and data science. So thank you, Kanak. Once again, I'll stop the